why don't we get going? We've got a bunch of people on, so fabulous. Welcome back, everybody. As you can see in some of the chats, it's a very windy day here in Colorado, and up at the Flatirons campus, the winds have peaked at over 100 miles an hour. So in the almost 50 meters per second space, and so it's a breezy day here at the Flatirons campus. So let's get rolling today. We've got a number of good presentations. So Brent, if you could go to the next slide. Today we're focusing on some of the kind of information that's really critical for people to understand within CIP that directly applies. So we have a presentation from Brent himself talking about the new ANSI standard. Some talk about test sites and certification from Dean Davis. And then Rick Damiani will talk about some of the tools that are available to use in the design of wind turbines and are being pulled, as you'll see, more into the standards. And then tomorrow we have procurement and accounting with Kindle, some design review and evaluation. So what are the requirements, and then some additional things. And that's where Scott Dana will be talking a little bit about services and stuff of that nature. And then at the end of the day, we'll have a dialogue around CIP goals and what we can do to improve CIP, which is always something that we're interested in hearing from all of you about. What can we do better? And then we're in a really different place in the industry right now than we were when CIP was developed. So are there new areas or different areas that we need to expand CIP, or we should think about expanding CIP into, now that we're focusing more on getting the technologies in the ground, given that we have a couple of good turbines out there that are certified and are in the cost space. And then obviously we have Q&A dispersed around the day. So I think that's it for me. Brent, if we want to kind of keep on schedule and jump over to your presentation on ACP.
All right, thank you, Ian. Thank you very much. Here we go. Yes, as Ian said, it's windy in this place behind me. And if this was a few years ago, we would be meeting in person, and this would be quite an interesting day. We might be at the hotel or virtual. But let me click one more button, and now I think we're ready. A little cleanup from yesterday's electrical standards presentation. I meant to acknowledge, Rob Wills acknowledged Robert Preuss, who has put in a lot of work in electrical safety standards and wind energy. I meant to acknowledge Joe Sposi, who also is steeped in this topic. He used to work with Intertech, and now he's a consultant in this space, as well as testing and certification. And Tim Scanina with UL, who has been working on UL standards and involved in small wind, distributed wind for a long time. Okay, on to the present topic. So we'll get right to it. Where are we with this national standard for distributed wind in the US? Well, back in 2009, there was a lot of activity and standards, testing, and certification. We decided as an industry we needed our own standard and our own certification body, and there was a big uptake in activity in this space. In late 2009, we had the AWEA standard, the AWEA standard 9.1 2009, and immediately was utilized by testing organizations and turbine manufacturers, designers, certification bodies. It became a pathway to eligibility for incentive agencies, and consumers use it for that as well. After some years of using the standard, we decided it needed a revision. So it went through a revision cycle, again with AWEA, American Wind Energy Association, through their Wind Standards Committee. So AWEA SWT-1 came out with some changes, but in 2019, following an ANSI, American National Standards Institute audit of AWEA's Wind Technical Standards Committee procedures, they found some issues with their procedures, remanded this standard, which went through that process and we've basically reverted back to AWEA 9.1. Now in 2020, AWEA joined American Clean Power Association, so now we go to meetings with ACP. And in 2020, NREL partnered with DWEA, the Distributed Wind Energy Association, to kick off a revision to our national standard so we could have some optimization included in our standard. We've had NREL hosted some meetings, and testing and certification was identified as great. We've come a long way, but it's become a bit of a barrier, and we need to work on the standards a bit, because that is, you know, the Bible, I guess. That's where all the rules are, and we all must follow the standards. So we have to work on the standards if we need improvement. So we worked with ACP, and we'll see who worked on it soon, but we are inches away from having a new revision to the standard. The new ANSI audit to their new ACP procedures went very well. They used this small wind turbine standard as the standard to for the audit, and watching it go, auditing as it went through the process, and it's now in the hands of ANSI for final publishing. And looking back to SWT-1, which really was lightly utilized, it was only out for a short amount of time. We were sort of in this transition period, and then it was remanded or withdrawn. But when we did this latest revision, we started from SWT-1, because in that revision, we had some good changes. The AWEA standard, as you probably know, points to the International Electrotechnical Commission, IEC standards for small wind, -2 for small wind design, -11 for acoustics, -12 for power performance. And many of those standards had seen a revision themselves. So we need to update the AWEA standard with some new ratings, a new consumer label that was in -2, and the acoustic standard had a new annex for small wind that we could refer to. We also added some informative notes throughout the standard to help with clarity and understanding of each step of the process. The conformity assessment or certification requirements were sort of mixed into the technical requirements, and in the standards world, that's a bit of a no-no, because you essentially test and design to technical requirements, and then a third party does conformity assessment. So we segregated those in the standard. And so we had a good starting point for our latest revision. So moving from SWT-1 to what is now called 101-1, ACP started a committee, and three chairs, myself, Jeroen van Dam from NREL, and Mike Berge of DWEA and Berge Wind Power. We also included a group of players to sit down and work on this standard, including Dean Davis, Ian Josposy, Ken Kodelik, who's I believe here, Robert Preuss, Tom Fleckenstein from Buffalo, New York, and Todd Hanley from Berge Wind Power, and Trudy. I'm sorry, you're missing a bullet, Trudy Forsyth, Wind Advisors team. We met in person in February 2020, which was probably maybe our last in-person meeting for a while. And we worked on the standard as a group, and then had several virtual meetings to resolve comments and finish it up. During this time, Jeroen had a great idea, which is often forgotten, is to get down on paper the thinking behind these changes, because we call it sometimes legislative intent. The intent, the justification, the background, the data analysis, the discussions can be forgotten and lost, and you just face with trying to understand this standard. So we published this NREL technical report found at this link here on OSTI that goes through these changes that I'll be speaking about in great detail, and the background that led the group here to the decisions that were made. One big change was increasing and changing the format of the scope. So previously, the standard followed the IEC 61400-2 scope of up to 200 square meters of rotor swept area. But that was leaving a gap between small wind and large megawatt scale wind, where turbines were being required to follow the large wind requirements, but they were much more like us, smaller scale distributed wind turbines. So we changed the scope to fold those in, and now turbines with a peak power of up to 150 kilowatts fall into this standard. And so peak power being the top highest bin average power in the power curve. And some of the reasons behind this, I think it was mentioned yesterday, specific power is trending down. In other words, rotors are getting bigger and driving swept area up even for smaller wind turbines. And it could take a turbine that is small yesterday and move it up to large tomorrow because of that 200 square meter limit. And we thought peak power is a pretty good way to define the maximum loads, especially with electrical and thermal issues. And there's some good debate going on, which we'll hear from Rick on the mechanical and aero loads. And if you look at that gap between small and megawatt, here's some examples up here. And they've got swept areas of 400 to 700 square meters, but they're all, 50 to 100 kilowatts in peak power. And so they seem to belong over here at the small wind table instead of over there in the multi-megawatt standards. And we also wanted to differentiate some requirements based on sub sizes of small wind turbines. And we decided it would be great to break that based on peak power. We made a slight change in the definitions of the reference annual energy, sort of a single number kilowatt hours per year you may expect with a Rayleigh distribution. We changed it from at 5 meters per second to 6 meters per second. And we in the distributed wind industry like to be conservative. We don't like disappointing the end user. So, but PV is more technical, and they say, hey, at this watts per square meters, this module can produce this. So we moved closer to what this turbine can produce and moved it up to a 6 meter per second rating. Really to help level the playing field as consumers judge between distributed wind turbines and other distributed energy resources, if that makes sense. And we defined micro wind turbines, a new definition, as up to 1 kilowatt. Power performance is a little bit of a change. It was doing a power performance test to the AWEA standard was already really pretty close to an IEC 61400-12-1 test, but there was some discrepancy between the wire run requirements, so we resolved that by just defaulting to the IEC requirement. We had our own AWEA requirement of taking the database further and further out to clearly demonstrate peak power. But we thought that was less of a power performance issue and more of a safety and function testing issue, where you want to make sure you clearly have tested and demonstrated peak power. So we moved that database requirement to safety and function, and then defaulted to the IEC database requirement so that you can know when to finish your IEC power performance test. And so this really made power performance testing to the American standard more optimized. And further optimization is not requiring a site calibration. These are small turbines. The Met Tower is not that far away as compared to large rotors. And so we thought, we may lose a little bit in accuracy, but save some in testing costs by not requiring that site calibration where you put an anemometer where the wind turbine will be, and you measure wind there and at your Met Tower for a while and come up with a correlation factor, which typically came out to be something like 0.98 because they're fairly close together. You still have to do a terrain assessment, but not a site calibration. On acoustics, the -11 standard edition 3 does have NXF for small wind. Slight misalignment with scope here in that this was a predecessor to our scope change, and they apply that NX2 turbines with a maximum power output of up to 100 kilowatts, which is the same definition as peak power. We changed the uncertainty calculation to a should. So you basically don't have to do acoustic uncertainty calculations, saving a little more in our optimization efforts. And it's not required for our new category of micro wind turbines. Okay, everyone okay out there? On strength and safety, so this involves a big chunk of the -2 standards, design evaluations. We made a few small changes here. Based on some work with an IEA task that studied turbulence and distributed wind, that data informed the team to raise the assumed turbulence intensity, average turbulence intensity at 15 meters per second in the design from 18 to 20%. Slightly more turbulent down there than down here where distributed wind turbines live than the standards were assuming. And we limited the simplified load methodology, which Rick Damiani will talk about today, to turbines up to 30 kilowatts. And we put in a table not recommended for turbines greater than 10 kilowatts. We limited the class, which is currently in the IEC world a choice of the designer class 1 for very windy locations, 2, 3, or 4, or S for special. We limited the IEC class to class 2, which should provide turbines designed suitable for most locations on Earth. If it's a particularly high wind design or particularly low wind design, then the designer must use to the ACP 101, use a class S turbine and set their own assumptions. And then we're not requiring a design analysis for micro wind turbines below a kilowatt. The duration test is, had a target on its back. We discussed it a lot during the revision of the WEA standard to SWT-1. Here's a word cloud of the discussions, and duration was a big concern. That debate years ago was between, should we get rid of the duration test now that we've evolved design methods? Big turbines don't have to do a duration test. The duration test takes forever, but others were worried about wiping or deleting the duration test because it does give the test site a chance to say the turbine operated reliably or not. But in many meetings across the world in these IEA discussions, the duration test was seen worldwide as a barrier to market entry, takes forever, and innovation because a change may force you back in the front of the duration test to do it again. So we wanted to study duration tests and learn how we could optimize it. So we looked at 31 reports from all these great test sites around the world from a period of 2007 through 2018. And the vast majority of these tests were done to the class 2 requirements, which we are now limiting turbines by default to follow. There was one, I think, Patty, this is you, one successful class 1 test. Actually, I'm not sure where that was. It might have been in Spain. But there were 3 class 1 tests that just could not meet the high wind, the hours at high winds required by the standard for those conditions. And the turbine had to settle for a class 2 duration tests. And as you can see, there were a few class 3 and a few class 4. One of the big problems with the duration test as it is now is we describe it as a 6-month minimum test. But looking back at these test reports, it can take much longer to complete. And so there are some dots over there, and that's the test period for the 31 studied reports. Put the red dots there as turbines that went into a duration test and made it far enough to actually result in a report that says it did not pass the requirements. But if you've got any experience testing your turbine or working at a test site, you know many turbines go for testing and fail quite early, and there is no duration test report. It's sort of like, okay, back to the drawing board. And we don't have a lot of that data. We would love to learn more about failures, but it's just not well documented. But we have this data, so we learned that one turbine had sort of a lot of small failures, which adds up to a lot of downtime, and it failed because it could not reach that 90% operational time fraction, basically more than 10% downtime. 3 failed after post-test. So 9-10 months later, you're finished with the test, you bring it down and you look at the blades and they're stress cracked, they're no longer have structural integrity. 3 turbines failed after looking at them post-test. And then 2, the turbine manufacturers learned a lot during the test, could not resolve things, and aborted the test. And some of these failures include inverters failing, broken welds, blade cracking, the vertical axis turbine exhibiting excessive rotor friction, tail damage, failed air compressor, and excessive faults leading to too much downtime. So you can see our 6-month tests can sometimes take up to 18.5 months to meet all the various requirements. So after the study, we decided to change the 10-minute averaging interval, which was unique to duration testing, to 1-minute averaging. This means your whole test setup is utilizing 1-minute averaging on your sample data, which makes things more optimized. And we require the turbine to demonstrate reliable operation through 10 hours of wind speeds of 15 meters per second and above. So it needs to see some time in high winds, and then overall 1,000 hours of power production. And I guess I'm sort of missing the used to be numbers, but it used to be 2,500 hours of power production, and then various levels of hours above wind speeds, including very high 1.8 times V average, or even 2.2 times the V average based on whatever IEC class was chosen. So this is a pretty dramatic reduction. So somewhere in between getting rid of the duration test and keeping it as it is lies a sweet spot, which we hope we got close to. Luckily, these test reports that we studied had tables, monthly tables of wind speeds and hours of power production. So we were able to do a what if analysis. Like, how long would these tests have taken per these new requirements? And, so as you're marching along turbine 9 up here, it's moving through a duration test that started in July 2008 and moved all the way through March 2009 before it was completed. With the new requirements, the requirements would have been met after 5.3 months, shortening the time of the test. So overall, if you look at this chart, the blue was the test, and the red is the potential, the estimated what if test period. And on average, for the test reports that had this data, the average test period went from 10.2 to 4.2 months. You know, we still require reliable operation, but we've changed how that's defined in the standard. So we've eliminated the requirement to calculate the operational time fraction. We've eliminated the need for analysis of power degradation and the observation of dynamic behavior. And now these things sound great, but when we analyze these test reports, not a lot was learned from these studies. So we're trying to make the test easier and shorter and cost less. And so we're defining reliable operation now as no major failures, no significant wear, corrosion, or damage to the wind turbine during the test. So you still have to do that post-test inspection, but you don't have to do these other metrics for defining reliable operation. Okay, micro wind turbines up to 1 kilowatt. We, you know, Denmark kind of led the way. They have their own separate requirements for turbines of roughly this size, but a power performance test to see what it does, safety and function test to ensure that it's has those features to limits rotor speed and power, and a duration test to assess its durability in some way. But no acoustics, no design analysis, no blade testing. With the relatively low cost of this technology, there's some allowance for a little additional risk of without significant financial consequences. So we really tried to trim the requirements down for this category. And so the validation of the design is really through the testing that it does receive. And as we'll learn about soon, the follow-on surveillance of a certified micro wind turbine. I see some questions which I will pay attention to when I finish. Yeah, if that's okay. The table, there's a table at the end of the standard that breaks down slightly different requirements in 4 subcategories: micro wind, 1 to 30 kilowatts, 30 to 65, 65 to 150. So we've talked about micro wind in terms of not requiring a structural analysis and then some testing. 30 kilowatt machines and down, you can use the simplified load method for this category, but it's not recommended for turbines greater than 10 kilowatts. And we've put through some basic minimum validation of the air elastic modeling, and required all the testing except for loads testing, and the blade testing is just static blade testing. And then slightly larger machines, they're not allowed to use the SLM to be certified to ACP 101, the simplified load model. And they have slightly more validation to do for their air elastic model. Still no loads testing required per -13, and still only a static blade test. Then the largest category, your air elastic modeling needs a little more validation through some measurement. Loads testing is only for validation of the models as mentioned above, and static blade testing is required, but fatigue testing is encouraged, but still not required. And so this is another change in our conformity assessment portion of the standard. We know that certification bodies are accredited to ISO 17065, and that they must do some sort of surveillance to maintain the validity of a certified turbine. And in the green is really what folks are doing now. A factory inspection showing that you have quality control and you're making the certified design. Annual reporting of all the design changes, field failures, complaints, warranty issues, and sales figures to know what size the fleet is, and then any significant changes or safety related major field failures are communicated to the certification body without delay. What we've added is this part here called field inspection. So installers, end users learn a lot about, well, let's back up. Test sites learn a lot about the turbine under test for certification. And then it's certified, and then it's out in the field. And now the installers, service providers, and end users actually learn a good amount from the field behavior. And we wanted to put a little more structure there so that 5 turbines will be monitored for 3 years. The installer, the service provider will keep an eye and inspect these turbines on a regular basis, following some routine inspection requirements already in the IEC standards, and provide a report to the certification body and the manufacturer on the status of the turbine and how it's going, and do an actual climb up and do an inspection for much like what you do at the end of the duration test for cracking, degradation, and significant wear. So we're almost extending the watchful eye of the duration test into a few samples in the field. And then to really just assess what kind of site was, what the conditions were at this sampled wind turbine. You report the annual energy production and an estimated annual average hub height wind speed at that site. So you can say, okay, this is a really productive site. It made a lot of kilowatt hours. It's a pretty windy site and it's held up well. And so we just want that information to flow back in an organized way to the certification body and the OEM for that 3-year period. Okay, so the standard is not out yet, but it's gone through all the major steps and all the public comment periods and all the audits, and it's now at the very end. Jeroen, Mike, and I actually just received a reformatted ANSI draft to make one last final check on. So it's getting really close. If you want to have a look at it today, you can just Google ACP 101-1 and it pops up there at that link, which is still up, which is a copy that is still up from the public comment period. And there's the link to that justification report. Okay, so I've saved a couple minutes here for these questions, and I will try to do that. Okay, Ian says there's one from Patty. Can I just confirm that ACP 101 mentioned yesterday is to be issued shortly, is the same as SWT-1? Yeah, so as you can hopefully have just learned, it's not. We at 9.1 evolved into SWT-1, and now there's a revision based on the old 2016 SWT-1, and we're calling this new one ACP 101-1, and that's mostly driven by AWEA's name change from AWEA to ACP. Can system certification be run in wind tunnel? No, I'm sorry. Wind tunnels are pretty good for product development, but it has to be out. The testing all has to be out in the wild and free wind. And there's some answers from Robert. Thank you. Josh says, for the duration test, if damage to a wind turbine component is found during the test, does the test restart and run for another period? It's no longer 6 months, but major failures do require a restart. And the standard does a pretty good job of listing failures to the major components, the rotor blades, the generator, the inverter, but not like a single device on a board, silicon carbide switching device. So there are minor failures and there are major failures, and that's defined fairly well in the standards, but it's also up to the certification body to make that decision. Tim, could you put the links in the chat? Yeah, sure, I'll do that. As soon as I get a breath. And Mr. Kogan, how to establish the rated wind velocity as a result of rated power? The standard standardized. So the large IEC 61400-12-1 has rated power at rated wind speed, which is not given, but this standard puts it at 11 meters per second. So what is the bin average power at 11 meters per second? That would be your reference power. Do all 5 sample sites have to be certified? They're just customer sites, and the end user is allowing their turbine to be part of the sampled surveillance turbines. And so there's no procedure to certify these sites. It's agreed upon, I believe, in the language. The turbines are chosen by the OEM and the CB, right? So here's your options. These people agreed to let the installer inspect them on a regular basis, and they choose from the list. And Scott's put in a link.
Just to be clear, and just to be clear, Brent, they don't have to have wind monitoring or anything of that nature. They certainly can, but that's not part of the goal, is looking at performance per se. It's more duration. And then there is a question, a hand up.
Okay, I can't see that. And so if you have your hand up, let me try to figure out how to get back to the.
You should be able to unmute yourself and just talk. Go for it.
Yeah, I do. Hi, my name is Don Simov, and I'm working on a working prototype. And my question for certification is, what if your prototype is made not on one turbine, but the turbine it's system of multiple blades and multiple size of blades, flexible, and how do we focus to what the prototype will be built so it could be testified or certified?
Mm-hmm.
I mean, let's say I can put in a turbine, it's a vertical axis wind turbine, and I can put multiple blades. Let's say I can put from 3 to 30 blades,
right.
And the different size, how could I focus on what the prototype will be good to certify and what we're going to certify from that?
Gotcha. Yeah, we see that a lot, and that's really a discussion with the certification body. You may have a family of turbines with different options, and what manufacturers typically do is say, okay, let's certify this one. It's our most common or highest selling, our flagship variant. And then the other variants could be certified as a family, but each one will need to be assessed individually. You can't certify one and then say, yeah, the 6-blade version of this 3-blader is the same, because it's just not. And that kind of assessment of a variance is something that's talked about a lot. In the new IEC 61400-2 standard, there is a new annex on variance, trying to tackle this issue, but it's if you boil it down, the answer is it depends, and you have to have a discussion with your certification body on variance.
All right. At one point, can we have a specific discussion on it, or so I can show exactly what I mean? And
yeah, you bet. Yep.
Okay.
Yeah, I've talked about that a lot because I used to work for the SWCC, and
because in this case,
the answer is it depends. So
yeah,
but yeah,
I'm
happy to.
That specific turbine can be tailored for any site. It's if there is the slow wind, you can add a little bit more blades, and that will solve the problem. All right, I'll send you email, and when you can have time, we can talk about it.
Okay, thank you.
Thank
All
you.
right, look, everyone, we have a little more question time after some more presentations, but we should probably move forward, if that's okay.
Sounds great. So why don't we move on to the next presentation? And in this case, it's Dean Davis from Windward Engineering, and then you, Brent, again. So hand it off to the two of you.
Yeah, and just to wrap it up for Josh, it's okay if you certify your turbine and you don't have 5 to be sampled. That's not a no-go for certification. It's just a method of surveillance. So if you've got 3, they'll survey 3 and wait for the other 2. And yes, DWEA and NREL have been in discussions with the Internal Revenue Service about updating the language in the code to mention this new standard. Okay. Thank you for your attention on that. I hope that's all good news. We'll see how it goes. Now, let me try to go with the next session 5. Oh, I'm sorry. I got to stop sharing because our friend Dean Davis is going to share his screen for this presentation. Dean, are you there? Dean's there. I see a screen coming. And Dean, I'm going to let you kick it off and show your background slide, and then I'm going to talk a little bit about certification body stuff, and then turn it over to back over to Dean. And Dean, we can't hear you, but now we can.
Okay, can you hear me now? Okay.
Yes.
Yeah, that was good, Brent. So, yeah, just a quick background. Been in the small wind turbine industry for a while now. Picture in the upper left there is me back in college. Built my first wind turbine and tested it. That was out in California. Came out to Utah to study under Craig Hansen. Got a master's and did a lot of research on computer modeling of wind turbines, and then set up the test site in Spanish Fork, really initially to validate some computer modeling work that we're working on. So that was back in the late 90s. Played around on the test site long enough that I thought I should do something on my own. So in 06, started Endurance Wind Power, played that game for about 10 years. That company ended up going bankrupt, and then kind of went back to consulting. And test site is obviously, we've got lots more equipment than we did in the early days. There's a shop and an office now, and telehandler and lots of stuff like that. So anyway, it's a little bit of my progression over the years.
Sorry, you'll have to listen to me for a wee bit longer. But I got into this business when I landed at Appalachian State University to go to grad school in appropriate technology in 2004. And they immediately put me in charge of the Beach Mountain Small Wind Research and Demonstration Site, where I ran that. And we did lots of small wind testing and torturing and training, and I met a lot of people and learned a lot. 2009, I was the technical director of the newly formed Small Wind Certification Council, which is now part of the International Codes Council. And then taught for a while at App State, but now in 2020, I've landed at NREL, and there's an exciting picture of working virtually. We're going to talk about testing and some, testing for certification as part of CIP. There are 3 topic areas that require the turbine to be tested. One is obviously prototype testing with some reduced requirements. And then there is certification testing for small and large wind turbines, which must be done according to the standards, because you're looking for conformity assessment here, certifying that the turbine was designed to and tested to the requirements in the technical standards. And so for prototype testing, I've done a bit of that. I would say the guidance is a little loose. You still rely on the standards, but you're not held to them by a certification body, but you want your data on wind speed and power to be reliable. But it's a relationship between the test site, someone like Dean Davis, and the manufacturer. It's like, what do you want to learn? Well, let's learn this. But certification testing's a next level move. And for small wind certification, we just learned about that. It used to be defined as turbines up to 200 square meters, but now with this new revision, it's folding in turbines up to 150 kilowatts. And that leaves our topic area of type certification. It used to be for turbines greater than 200, and now it's for Also, turbines that don't choose, that may be greater than 150 kilowatts and less than 1,000 square meters, they would fall outside of both the -2 standard, the OEA standard, and the new ACP 101 standard. And if they want to be certified, their option would be type certification to the IEC suite of standards. Or like Jeroen mentioned yesterday, if you want a globally accepted certificate to the international standards, then there is no bottom to the -1 standard. You can choose, a small turbine can choose type certification path. But as you can see from the figures below, just to get an idea of your price participation, I mean, I don't really know how much projects cost will be, but if it were to be in the range of $300,000, then you would be contributing $63,000 in price participation if you maxed out a $250,000 award on that topic. Certification testing, if it was in that range of project cost, then your cost share would be around $48,000. And the NREL amount 190 or more if you're doing listing, or more if you're doing loads. And then type certification could be $1 million endeavor where you would have to contribute $200,000 of that. And you're getting a sense of the requirements for certification, but it's really two things: design evaluation and test reports. So the design evaluation, we'll learn a lot about those methods next from Rick Damiani. The required field tests are a power performance test, acoustic, safety and function, and duration. The dirty details of all those live in various IEC standards. And then you may have a national standard like ACP 101 that makes some optimization changes to those requirements. Type certification, Jeroen has spoken about a little bit yesterday and again will on Friday, but it's heavier on both testing and evaluation. There's a design basis evaluation and there's a design evaluation. Still same power performance test, very similar safety and function test, but now there's mechanical load measurements to verify or to validate models, and both static and fatigue blade testing. And now acoustics, you know, they don't put huge wind turbines next to the barn as much as they do small wind. So acoustics is an optional test for type certification. There's a prescribed manufacturing evaluation as part of the certification, and then a final design evaluation, all involved. And so you can see why it's closer to $1 million effort. It's a pretty heavy endeavor. And here's some of the standards. It's an investment. They are copyright standards developed by global experts and published by various standards making bodies such as the International Electrotechnical Commission. The conformity assessment work is now under IECRE, the IEC Renewable Energy Certification Scheme, and they have produced ODs, which are operational documents. There's an OD for the type certification of wind turbines, and there's a brand new operational document, OD 554-1, I believe, that has just come out of the small wind turbine stakeholder group that paves the way for a methodology of global type certification for small wind turbines under 200 square meters. Power performance is to the -12-1 standard, acoustics -11, and then there's the -2. We just learned about OEA 9.1, ACP 101-1. The 61400-1 standard applies to all scales of wind turbines, but it's mostly for large wind turbines, or utilized for large. We'll learn more about mechanical loads from Dean according to -13. Rotor blades are tested to -23. Test sites are accredited by a third party to ISO IEC 17025, so that if they want to do accredited testing, that's the standard. Your quality management system in your factory, ISO 9001, and then there's more for gearboxes, electrical that we learned about yesterday, lightning, and so on. And if you're interested in being certified, you need to develop a relationship with a certification body, and there are a few listed here. And as Dean put in here, engage early to avoid surprises. It's kind of a long-term relationship with a lot of back and forth communication. And I think as Mike Berge expresses it, there's a lot of internal engineering time proving to these bodies that your design meets the standard. So it's quite a bit of back and forth. Now, Intertek used to be active in this distributed wind space, and they still are in listing, but less so in the turbine certification world and testing. The main still active player in small turbine certification here in the US is ICC SWCC. UL does do testing and certification. BSI is listed as having certified turbines in the UK. DNV does large wind. SGS is international certification body. Class and K is just in Japan, and they're all accredited to ISO IEC 17065. The test sites in the US have waned a bit. There used to be one in Kansas. It shut down years ago. The App State Beach Mountain facility is now closed, essentially. The Intertek has shut down their small wind testing in Cortland, but these 4 remain. 2 up in the Windy Panhandle, 1 by UL, and 1 Renew test site in Pampa. Here's the NREL spot in Arvada, and then there's Dean's site in Spanish Fork, Utah. And finally, my last slide. So if you have your testing for certification done by an accredited testing laboratory, then essentially the certification body says, great, then there's already a third party evaluating that testing. Just send us the test reports. But a lot of these sites are non-accredited. The only one on that page that is accredited, assume the scope is still valid for this work, is the NREL site in Colorado. A lot of sites are not accredited. It's a major endeavor, and if they're not, you're still able to participate, but the certification body does witnessing. So they show up and check the quality assurance procedures and manuals of the test site. They witness the testing as it's happening. Interview the personnel to ensure the testing is done to the standards by a suitable and qualified organization. And maybe some sort of round robin or other method of evaluating the data processing tools of the sampled data. But the goal here is to make sure that the results of the testing meets the standards, as well as the basic quality control procedures as outlined in ISO 17025. Okay, thank you very much.
All right, can you hear me?
Yeah, we heard that, Dean.
Okay. So thanks, Brent. So I'll take it from here and kind of just give you details from kind of more of the details within the standard specific to certain tests, as well as, throwing in some of my experience over the last 25, 30 years of doing this kind of work. So obviously, if you're going to take this on, you need to have a test facility. Now, that doesn't mean you have to go to one of those on the map. You're welcome to do it at your own facility. But I kind of outlined, if you could pick an ideal test site, what would it look like? So generally speaking, for the field testing, regular and non-seasonal winds. Obviously, you don't want to set up your test and then have to wait 3 months during the summer while there's no wind to really get going. Favorable zoning and permitting laws. And then I found nearby resources, heavy equipment, hardware store. That's convenient. You don't want to be so far out in the middle of nowhere that, you know, a bolt is going to take all day to acquire. So for power performance, ideally you have unobstructed space, you have flat terrain, and then you have occasional high winds. Now that's a little less, the power performance really used to require you to capture those high winds in the power performance. And as Brett said, now it's kind of shifted into safety and function, which I think is a good thing. It probably belongs there more. In terms of acoustic, quiet site, unidirectional winds, the microphone has to be kind of in the general downwind direction of the turbine. So if your wind directions are moving all around, you got to move that microphone all around. No nearby reflective surfaces, and then unchanging ground cover. For us, snow is the main factor there. In terms of duration testing, lots of power producing winds. You don't really need extreme winds. And I think this is not required within the standard, but some variability in the ambient temperature, I think, is probably ideal. You know, if the turbine is going to show some different behaviors in hot or cold temperatures, it'd be nice to know that during the duration test as opposed to on a customer site. For loads, you do want those occasional high winds. That's going to be some of your more interesting loads. Regular times of calm, I say that because you're going to need to be on the calibrations somewhat regularly. And this, you know, if you were actually doing a -13 test, you need some variability in turbulence. And I said here, the ideal site may not exist, but most shortfalls can be mitigated with ingenuity, time, and money. So, you know, you can have a test site that's pretty good, but it lacks in some, but you can figure it out. You can make it work. In terms of the assessment, some sites would pass all requirements easily. I mean, if this was your test site, you could just go through the standard and within Excel show that there's no issues. Some will require a little bit of analysis, and you'll have to exclude some sectors and do that kind of analysis. Others like ours, which is very compact, lots of different terrain features around it, lots of turbines around, used to require site calibration, although now in terms of ACP 101-1, you can bypass a site calibration, as Brent said. Really, I think, I mean, even in our complex site, our calibration factors were always 0.99, 0.98, 1.01, something like that. So very close to 1. So in terms of setting up your equipment, really, I consider the power performance to be kind of the gold standard. So if you kind of, you know, you're going to need to do, more than likely you're doing power performance. Certainly if you're certifying, you need power performance. So you might as well set up to the power performance standard, and then that anemometer and that Met tower and all the features of that are just going to be used for acoustics, for duration, for safety and function, and it's all going to be more than you'd actually need for those other tests. So a basic setup is going to be like shown here. You're going to have Met tower. You're going to have a primary anemometer at hub height. You're going to have a secondary anemometer, which is just below it. The standard specifies all the details on how far below you should have it, what boom lengths you should have, the size of the booms. You're going to have wind direction, air temperature as well, and then air pressure. For power performance only, you're essentially going to have, you know, a power transducer. That might include VA, watts, current, other things like that. And then you're going to need some kind of data logging or data acquisition system. I've been using National Instrument. That's their chassis, and there's modules you plug in there. And then obviously, eventually it's going to end up on a computer. There's going to be other measurements you're going to want to do for power performance. Now, I think in the standard, it's a should. So I think these are technically recommendations, but more than likely you're going to have rotor speed. It's convenient to have turbine status. If it's variable pitch, you're going to want pitch angle. If it's furling, you're going to want furl angle. wetness, rotor azimuth, etc. And it kind of can grow out depending on what you're after and what you really want to find out. This was a quick and dirty list I put together for just giving a rough number on if you went out and bought all this equipment, instrumentation, as well as maybe a small data shed and a Met tower and stuff like that. You're kind of into it in this $24,000 range. These are old prices. Nowadays, maybe we've got a 10%, 20% increase with inflation going on. But that gives you a ballpark. Obviously, you could spend a lot more. Probably you could spend less as well. All this instrumentation is going to come with calibration sheets. That's an important part, you know, for your report. So you're going to need these calibration sheets. The constants that come on the sheet are going to be used to basically turn your signals into engineering data or engineering units. There's uncertainty within these calibration reports that'll go into your uncertainty analysis. The calibration sheets end up going in kind of an appendix in the final report. And then again, your certification body might have specific requirements around the calibration. So you'd want to check with them and make sure that the calibrations you're going to get are of a high enough quality for them to okay that. In terms of how much data are you going to need to do a power performance? And this is a little different because again, a lot of that high wind used to be captured in the power performance, and now that's moved over to the safety and function, which I think is good for AEP calculations and that kind of stuff. The high winds really aren't a big driver. So if you're in 61400-12-1 edition 2, Annex 8, which is for the small wind turbines, you need a minimum of 10 minutes in each bin. The bins are filled with 1-minute data sets, and the bin width is 0.5 meters per second. And you're going to need to fill a range from 1 meter per second below cut-in to 14 meters per second. And in total, you're going to need to have 60 hours. If you're not within that Annex H, within -12, a little bit more in the requirements, but you're going to need a minimum of 30 minutes in each bin. You're going to need to go again from 1 meter per second below cut-in, but now you go to this slightly higher wind speed more than likely, which is calculated based on rated power. And the total data set is now 3 times larger at 180 hours. So how long does it take? Obviously that depends a lot, but it used to be sensitive to, you know, the sectors that were valid. You had to have all your winds coming from those valid sectors. Well, ACP kind of opens that up and says the excluded sectors are now allowed as long as the anode is not affected. So obviously you can't have a sector where the anode is behind something, or in particular behind the wind turbine. And then usually on a power performance, you find that you get a rough power curve pretty quickly, but you might wait around to fill in those higher bins. Even 14 meters per second, you might end up waiting around to fill those bins while the rest of it is pretty full. NREL suggests 3 to 6 months. It can be performed along with a duration test. So you might, you know, the duration test is probably going to take longer than the power performance. So you kind of be getting those two at the same time. In terms of post-processing, there's, you know, my feeling is it can be easily performed in Excel. I used a lot of array functions when I was doing it, and it might be slow on a really slow computer, but it's not that intensive in terms of data processing. When you go through the standard, it uses clear and well-defined equations. Here's an example for coefficient of power. But again, you know, they give you the equation and they tell you pretty clearly what each variable is within the equation. So overall, the standard is very clear and how to do these calculations. That said, there are a lot of details, and it's difficult to imagine that if you put a spreadsheet together and you had your buddy do the same spreadsheet reading through the standard and you compared notes, I'm guessing you'd probably have some differences somewhere. So The uncertainty portion is probably the trickiest part. And I said here that there's NREL reports have details on their uncertainty analysis. So those are good resources. And there are some old NREL presentations where they detail the uncertainty part as well. So those are good resources. In terms of the report itself, the standard has a section on what must be reported. And then I think the NREL reports, which you can just download off the internet, are a great template. It really shows you, they're going to be following the standard. The standard already tells you what to do, but it's really nice to kind of go through and see what's exactly in the report and how they presented it. And just as a quick example, some of the reports I downloaded from NREL, like they're 50 pages roughly in total length. About half of that is kind of the report and the data, and then the other half are appendices like the calibration sheets, stuff like that. And here's just a quick example of a power performance, a final power performance scatter plot of one I did on a 50 kilowatt turbine. So moving on to acoustics. The good news is, as I said before, most of the instrumentation is now in place. So you've got the wind speed and pressure and temperature and all that kind of stuff. The test times are also much shorter. The bad news is there's significant challenges in collecting the data, which I'll describe a little later. The data processing is much more difficult and time consuming. And there is some new instrumentation. So personally, Windward spent about $11,000 on a microphone, a calibrator, noise lab software, and DAC equipment. Within the acoustic standard, there's an Annex F for small wind turbines, which they specify as less than 100 kilowatts. So focusing there, they want you to capture the acoustic characteristics from cut in to 11 meter per second as a minimum. And then that says within the standard if possible up to cut out. In particular, if you have a turbine like that furls or that flutters or something like that, it makes sense that the acoustics can be quite different in high winds. The measurements are 1 second each, 1 second each. And each wind speed bin within that range, with a bin width of 1 meter per second, you need 12 measurements. So again, it's not a lot of data. That's 2 minutes per bin. The way it works, you'll end up getting more in some bins and harder to get other bins. But as I say here, it's not a ton of data, but it can be challenging to get. That being said, it's still likely it's weeks, not months, in terms of data collection. The microphone, as I mentioned before, does need to be roughly downwind from the turbine. If you're greater than 100 kilowatts, it's a little tighter. If you're smaller than 100 kilowatts, I think they assume, which is often true, smaller wind turbines are more active in yaw. They give you a little wider leeway there. The measurement chain needs to be calibrated before and after each measurement. And ideally, you want the same conditions for the background noise and with the turbine operating. The way I did that in a lot of setups is I'd run the turbine for 30 minutes and then I would shut the turbine down for 30 minutes. And by doing that and then I turn the turbine back on and run it for 30 minutes and then off for 30 minutes. And so by doing that, you're really, as best you can, you're getting the turbine operating in the same conditions as the background noise. And then obviously it has to be quiet. People, traffic, birds, planes, trains, grass, crickets, etc. To be honest, I deal with all of those essentially at my site. All of those, ideally you don't want them. And it's crazy when I'm out here in the middle of the night, like everything makes noise. I mean, that picture is just an example of some vents on a nearby building. And in the wind, those things are just flapping and making noises. So I go out there and duct tape them closed during the test. In terms of software, we use Noise Lab. You're going to need somehow to basically take the recordings and turn them into dB numbers. For full automation, you're gonna, use a packaged software or something other than Excel. You can use Excel, that's how I do it, but it does result in complicated spreadsheets. And as far as I've gotten it, I have not gotten it to just throw the data in and let it run. It requires me to go in and work on different things, a little bit of manual manipulation. And I struggled with my computer. So I actually built like a, almost like a gaming computer to really help speed up Excel. Like the power performance, the standard uses clear, well-defined equations. But the equations now are much more complicated and easy to make errors. We've struggled a little bit. We've done some round robins, and sometimes the wording within the standard can be challenging, where we've had differences because we interpret some of the words to be different. And then I think the other thing that makes this one challenging is most of us don't have a strong background in dBs and sound power levels and that kind of stuff. So it's harder to recognize problems in the data when you just, they're numbers that have less meaning than other things, other numbers, versus kilowatt or something. Kilowatt has a meaning most of us can make sense of. For this reason, I said the data analysis absolutely needs to be validated. So when I put together my spreadsheet and my analysis, I had another engineer doing the exact same thing. And then we're constantly just putting in the data and coming up with the answers and then comparing. Tonality is laborious and requires lots of manual clipping and recordings. I used to figure tonality was half of the labor in doing the acoustic reports, but the ACP 101 got rid of that. So that's going to be a big time saver and a lot of effort taken out of certification, as long as you're in that, and as long as you're trying to do it to the ACP standard. Significantly more difficult than the power performance overall. So duration testing, here I'm going to really focus on the ACP 101 because it's got some changes versus where we were before, and I think those are important, and it should really simplify the duration test for people. The purpose is structural integrity. I could have added in here infant mortality, although maybe you'd find that out in the power performance and other tests. But material and performance degradation, quality of environmental protection. Used to talk about dynamic behavior, but I think the ACP is kind of lighting the emphasis there. In terms of requirements, Brent talked about this a little bit. Reliable operation now versus it used to have this operational time fraction and greater than 90% availability. Used to be at least 6 months. That's no longer a requirement. Used to be 2,500 hours of power production. That's been lowered to 1,000. And then it had these requirements around high winds. And that's what really drew out the duration test. So those have been eliminated. And to some extent, those are captured now in the safety and function, which I think is probably where they belong. Used to be 15 hours greater than 15 meters per second. That's been lowered to 10. Major failure will restart the test. And then the operational time fraction analysis power degradation is not required. So safety and function. Bottom line is kind of review, as a basic level, review of O&M procedures and other manuals, review of personal safety topics, warning labels, that kind of thing. In terms of the function side, kind of like a commissioning, but with some instrumentation. So you're actually doing some commissioning, but you're also able to kind of log RPM and stuff like that. You'd probably want to put the turbine through the basic fault conditions, grid fault, maybe pull a sensor, or have a sensor intentionally fail a sensor. And then you might be interested in looking at some specific events. Obviously, you'll probably want high winds, startup, shutdown, that kind of stuff. And then this is where now the safety and function is capturing some of this peak power limitation or regulation, and rotor speed regulation. So that's now kind of captured in the safety and function. And running through that a little bit. So in terms of peak power, you're going to find your peak power. You're going to go to 95% of peak power and find your wind speed. And now you're going to say 5 meters per second below that, 5 meters per second above that. We're going to want to see what the turbine does in those wind speeds. So you're going to want 10 1-minute data points in each half meter per second bend. So again, this used to be captured in the power performance. Now it's captured in the safety and function. And to be honest, there's still overlap there. Obviously, as you're doing a power curve, you may end up having this data as well. And for that matter, this will also demonstrate power regulation in this data set. For maximum speed, the standard says you want 2 hours of winds between 10 and 20 meters per second. So not a lot of time, but you do need to see those winds. And then you need 30 minutes that are below 15 meters per second and 30 minutes above 15 meters per second. And then you'll use that data to extrapolate or interpolate to this VREF, so out to these higher wind speeds. Mechanical load testing. This is something you'd be doing if you're doing a type certification, but you may do it even for just for a certification, even of a smaller wind turbine, really related to validating your air elastic modeling and that kind of stuff. So here I said it's not typically needed for the certification testing unless you're going to validate some loads in your air elastic modeling. It is necessary for the large wind turbines or the type certification. It can be a significant undertaking. Obviously, there's degrees of that. You could just put one sensor on, and that's probably not going to cost you $100,000. But if you were to do a full loads test, it's a significant thing. You can use, again, that power performance instrumentation for your wind speed and density and all those other parameters, wind direction. But now we're talking about adding loads to the tower, to the rotor, to the blades. There's challenges around getting the data off the rotating frames. So you may use slip rings, telemetries. I guess you can do some data logging on the rotating body as well, and then download that nightly or weekly or something. The standard talks about anti-aliasing modules being required. And then more likely you're going to have these other parameters like rotor azimuth, yaw angle, etc. Even if you maybe didn't have those before, but when you get into loads, that's going to help you to really do the post-processing of the loads. The standard around mechanical loads testing is -13. Talks to the minimum required data channels, assuming you actually wanted to come up with a full mechanical loads report at the end of the test. You would have these minimum channels. They have recommendations for additional channels. They talk about the load, the matrix or the metrics of the loading, transient load cases. You're going to want braking, high wind, shutdown, grid loss, startup, etc. Normal operating, it tells you what you need in terms of data sets per wind speed, the range of the wind speeds. They want turbulence variability in the wind speeds. The standard goes through to the calibrations, how to calibrate these strain gauges in particular. And then like the other standards, it talks about the data processing and the reporting. So in summary, this was, again, this was done a couple of years ago. Things probably got more expensive, but just a rough ballpark of time required and kind of some of the costs around some of this effort. Obviously, like I said, time and cost could vary significantly. And kind of further going along the summary, if you're thinking about certification testing, I came up with numbers, the field testing, about 175K, certification body, 35K, so a total right around 200K. And then, as Brent mentioned, type certification, quite a bit more expensive. We actually started on one, and we were just over $1 million, or just under $1 million, I think. But field testing, $250K. Other tests, so that's the blade tests, and a few other tests that probably are going to be involved with. And then now the certification body takes a much larger role in the project, so their costs are higher. So again, that's how I ended up with that, roughly $1 million. That's all I have.
All right, thanks, Dean. Excellent. One thing I just wanted to point out, you did, the IEC standards do have a should on the rotor speed, but the ACP 101 makes it a shall in the safety and function section.
Oh, okay.
Rotor speed measurement.
No, good enough. Yeah. Yeah, I would think it's pretty normal that you would want that. So, and
well, let's see, what time is it? It's 1:30, and we have a scheduled break at 1:30.
Yep.
So,
yep. So perfect timing. Any questions for Dean or Brent about this whole question about testing for the certifications? I mean, I think it's fairly clear that having someone who understands certification and all of this, either on your team, and whether that's within your company or organizations that you engage with, to help you, that is independent of the certification body. So someone who is sitting with you, helping do all of this, so that you're sure that the information you're collecting, whether it's at a laboratory or something like that, or a testing facility or something like that, all the documents you're pulling together is going to be what the certification agent needs and wants. The last thing you want to do is get into, I don't want to call it a bring me a rock, but you do a lot of testing and you hand something to the certification agent and they say, oh, but you need this, and then you don't know it. And you have to go through that whole process. So having people with experience, if you're thinking about certification on your team, is going to be important for success. Any other questions? Going once, going twice. All right, let's plan to take a break, and then we will come back in 10 minutes at 40 minutes past the hour, whichever time zone you happen to be, and then we'll get a presentation on design tools for distributed wind. As Brent indicated in his presentation, we're relying much more on design tools as part of these certification efforts, especially for the turbines above about 10 kilowatts. So a lot of work has been done over the last year in this area, and Rick is going to bring us up to speed on that. So the lines will stay open. Go grab a cup of coffee and wander back once you have that, and we'll be here. Thanks, everybody. All right, why don't we dive into it? It's the top of the hour, so welcome back, everybody, to the CIP 2021 workshop. Diving into the last hour or so. And so we've got another presentation from Rick Damiani, focused on design tools for the distributed wind industry. And then we'll have some wrap-up time for kind of general Q&A about topics of the day or anything else. So again, please keep yourself on mute unless you're chatting. Put your questions in the chat function, and then we can address those when we get to the end. And if people want to voice their questions, definitely raise your hand. That's been working pretty successfully. So without further ado, Rick Damiani, who a former NRELian, but also someone who's been working in the distributed wind industry for numbers of decades now, including turbine design at all scales and testing, a whole bunch of things. But most recently has been doing a lot of work, well, has always been doing work in design tools, but it's spent a lot of time recently looking at it at the distributed wind industry and understanding what gaps we have. So without further ado, Rick.
Thank you, Ian, and thank you for this opportunity. Thank you, NREL and DOE, for letting me participate here in this workshop. I'm very delighted to be back. I remember being one of the initiators of this program about a decade ago while I was at NREL, and it's just great to be back and seeing so many familiar faces too. I want to also acknowledge some contributions by Brent and Dean Davis and Robert Preuss to these slides that in a way or another have been presented in the past throughout the CIP history. So this is the outline of my talk. We'll touch upon some aspects of the wind turbine design. Of course, I cannot cover all of the multifaceted and complex aspects of the design, but I will focus on the options for loads analysis, and I will touch upon simplified loads modeling, and then focus a little bit more on aeroelastic modeling, which is really the core of this presentation. I will also highlight some recent work and results of a study that Dean Davis and I have been involved with NREL for the past years on aeroelastic modeling and interface to standards. I will also speak a little bit about verification and validation and why that is important for aeroelastic modeling as well. And then before discussing some final remarks, I will talk about the general workflow for aeroelastic modeling processes, and in particular, dive into the pre and post processing phases of an aeroelastic model process. I like to start from this slide that illustrates the difficulty or the complexity of turbine design, even though you may concentrate on the primary components listed here, from blades to the drivetrain, so hub through the generator, and the connection to the tower through the bed plate, and the control system with its subsystems and the pitch and the yaw systems, and of course the tower, the foundation. You can see how many key disciplines are involved in the design of these components. And they go from aerodynamics all the way to electrical and geotechnical engineering, of course. But what is really important here is to understand that a turbine is a system. And so it should be seen from a systems engineering standpoint, where the design of one component will actually have a big impact on many other components and on the overall product outcome. Of course, we can follow some established or industry accepted design standards or guidance, but you can imagine that the design of a turbine or the analysis of these components require quite a bit of expertise and experience in this field. If we focus on the current edition of the 61400-2 standard by the International Electrotechnical Commission, you can see there are at least 3 pathways that you can follow. At least these are the 3 allowed to reach certification under that standard: the simplified loads modeling, or SLM, the aeroelastic modeling, or AM, and the loads measurements. You've heard a little bit about loads measurements from Dean, so you understand how complicated that could be also, and the requirements for an accredited or at least a verifiable test site and the skills that go along with that. I will speak a little bit about the simplified loads modeling that allows you to examine a reduced number of DLCs, or design load cases, that are simplified also in nature, and also have a number of simplified loads equations that you may use to arrive at least a crude picture of the loads on your turbine. And then we'll focus more on the aeroelastic modeling in the rest of the presentation. Just a couple of words about full-scale measurements. Of course, refer back to what Dean talked about in his previous presentation, but I want to highlight that the standard requires that the load measurements be taken under conditions as close as possible to the aeroelastic model DLCs. And this statement actually is quite difficult to achieve at most sites. So it requires an appropriate testing facilities with an inflow of a certain quality, and of course the expertise that we heard from Dean in terms of load extrapolation, for example, and how to arrive at design loads from your measurements. As a term of reference, the big guys, so the utility scale turbines, use load measurements exclusively for model validation, but the design loads are really extracted from validated models. So turning now to the SLM, it's still a valid model for design, at least under certain caveats. The current standard allows you to use the SLM if you are within 200 square meters of rotor swept area, or RSA. And if you have a relatively rigid turbine, which means having a rigid hub, no teetering hinges, for example, no independent pitch control either. It provides key loads for key components, but it leaves you with a lot of gaps. In particular, you don't have a clear picture of simultaneous load contributions to a certain component, what we call simultaneous load component table, for example, that I will mention later in the aeroelastic modeling section of this presentation. So you're left with the need for using good judgment, good engineering judgment, to try and understand better the loading picture. Overall, you don't get a very good understanding of the coupling, of the various dynamic coupling issues that may occur in your machine. And therefore, you're forced into being fairly conservative, not only by using higher partial safety factors, but also by looking at using worst case scenarios. So adopting the extreme load contributions simultaneously for each component, which may not be the case. And of course, this will lead to an over-design turbine, generally speaking. But with that caveat, again, it's still a viable pathway to the design and certification of a turbine. I want to highlight, though, that you still have to rely on some test data, especially for parameters that are used as inputs to the simplified loads equations, such as design maximum rotor speed, power, yaw rates, and shaft torque, for example. Now, turning to the aeroelastic modeling here, I want to highlight why I consider it the primary tool for structural and performance assessment. First and foremost, it allows for a much deeper understanding of the response of the turbine from both a performance and a loading standpoint. It also allows you to span the design space, both in terms of design variables, so changing geometry, for example, as well as changing control parameters. And at the same time, it provides you with a solid and robust basis for design and certification. And then you can use your results also to streamline the conformity assessment that may follow a change in the turbine architecture. There's a caveat, of course. Aeroelastic modeling historically has been well tuned for more traditional horizontal axis wind turbines, or HOTS, and less for, say, vertical axis turbines or more exotic configurations that include airborne wind energy kites, for example. Some of the results that I'm showing here in these slides and some of these conclusions also come from the study that I mentioned earlier, the Damiani and NREL have been involved with in the last year, and that is going to culminate in the publication of a paper that's forthcoming. And I would encourage you to keep an eye out for that publication. Some of the advantages of aeroelastic modeling include the possibility of capturing three-dimensional effects, both from the aerodynamic standpoint and from the structural dynamics standpoint. For example, it allows you to capture unsteady aerodynamic effects, and it allows you to capture mode coupling between different components. As you see in this animation, for example, we have coupling between a tower fore aft bending and a complex rotor flapwise bending mode. It provides overall a very comprehensive picture, both from a ULS and an FLS standpoint, which means it allows you to capture hard to measure in the field extreme loads, and it allows you to understand what the fatigue damage in the various components might be. And therefore, you can remove that unnecessary conservatism associated with SLM. And it allows you also to, again, like I mentioned before, it allows you to span the design space to arrive at an optimal configuration. Here's another example of some of the conclusions of our study. As you've heard, ACP is now coming up with a new breakdown of categories for load assessment based on peak power. If you look at the table here in the lower left of the slide, you can see 3 turbines that are associated with very different power ratings and therefore peak powers, and yet they all present the same size in terms of rotor swept area. From an elastic modeler perspective, when we see a certain dimension and certain characteristics of the blades in terms of inertia and structural dynamics, of course, you immediately think that they will probably behave very similarly. They might have several aeroelastic issues that are shared across all the turbines. So is peak power really the key metric to use to differentiate when it comes down to load assessment? Dean and I have spent quite a bit of time and have come up with a table that you see here on the right-hand side of the slide that proposes a breakdown in terms of both rotor swept area and turbine archetype. And then you can see the color codes there that indicate more or less the recommended path towards a load assessment. And that means that your turbine may fit well within the SLM bin, or that you may need aeroelastic modeling, and with different levels of validation. Verification and validation is something we'll talk a little bit more in this presentation as well. But again, if you're interested in some of these results that may also trickle down into the future editions of the standard, please look out for that publication that is forthcoming. So assuming that you're fond of aeroelastic modeling, or that you have decided that your turbine fits in that category for your load assessment and design, you have at your disposal a number of different tools. You can see them here listed, at least some of them. They go from open source to commercial tools. And some are really focused on the design of turbines, in particular of hot turbines, and some others are more generic. They are multi-body dynamics codes that allow you to simulate more sophisticated or more exotic configurations, less than traditional, let's say, including vertical axis turbines, including airborne wind energy kites for that matter. Common to all of these codes, however, is a workflow that here is summarized in these various steps that are highlighted in these boxes. Not necessarily in this order all the time, but this is a good representation of what the main tasks involved in aeroelastic modeling might be. The first and foremost is pre-processing. Here we accumulate information in terms of, first and foremost, airfoil aerodynamics. So we have to come up with a representation of polar curves, just like those you see here in that graph. But additionally, you want to also have a description of unsteady aerodynamics for the various airfoils that your lift surfaces use. And then, of course, you also need the representation of inertial and structural properties. So stiffness, for example, distributed along the span of the tower or the blades and of other components, for example, the drivetrain and the yaw system. And then you put all this information together into a format that is compatible with the model or the code that you will be using. And this is what we call the input deck creation for your model. And the next step past that is that of a preliminary validation. This is where you make sure that your model runs and gives acceptable output, especially in terms of overall properties such as the inertial characteristics, eigenfrequencies, steady state, power, RPM, things of that nature. In parallel, you should have worked on a design basis that includes both the description of the environment, so primarily the wind. And so you would have created wind files with certain levels of turbulence and using certain spectra for the turbulence description, as well as the selection of DLCs or design load cases. And for that, you may follow the guidance of the standards. In the upper right corner of the slide, you can see the DLCs indicated by the 61400-2 standard. And then in earnest, you're ready to run your simulations. And we're talking about hundreds, but more realistically, tens of thousands of simulations, including some iterations that will produce tens of thousands of time series, just like those represented here on the left-hand side that are specifically for an extreme operating gust case. So once you have completed your simulation runs, then it's time to post-process them, which means extracting driving loads for both ULS, so ultimate limit states, and SLS or FLS, so service and fatigue limit states. You're looking for loads, you're looking for deflections, tip blade, blade tip to tower clearances. And of course, you also want to assess the potential for resonances or risks of instabilities. And we'll talk a little bit more about that. Now, that's pretty daunting, of course, and we've been working on trying to at least provide a starting point by collecting a number of aeroelastic model templates that could be used to build your own model. These templates cover a pretty good spectrum of the current market archetype and range. So as you can see here from this table, we cover quite a few different archetypes with these template models. Yet there are some notable missing in action players like a VOT model. We're working with NREL and Sandia National Laboratories toward the issuing of a VOT, both code, aeroelastic code, as well as a model that we could use and propose to the industry as a template as well. We're also working on potentially creating load reports for these template models that can be used to cross-check in a validation phase, for example, or V&V phase, your own model. So you would have both a template to start with and then a load report that you can use to cross-check your outputs. And I talked a little bit about verification and validation. What do we really mean by these two terms? Verification implies verifying the accuracy of your software. You would be involved in that if you're using your own piece of software to design your turbine and to go towards certification. You have to prove that your software has the correct implementation of the physics model that you've come up with, and that there are no gross bugs, that the math is implemented correctly, substantially. And to do that, you verify the performance of your code against some established test cases. So some benchmarks that are common in the literature, and quite often you do that by cross-verifying your code against established codes. More than likely, you'll be using one of those codes that we listed earlier that are already somewhat established in the literature and in the industry, and therefore you'll be more involved in the validation phase, where you will need to validate your specific input deck within that code to prove that your model represents the reality of the wind turbine physics that you're trying to represent. This is done in concert with consultants, with entities like NREL, but ultimately with a certification verification agency that will provide the stamp of approval. The goal is really to prove that your model is capable of predicting, say, loads and the response of the turbine as should be seen in the field. Now, of course, this requires loads testing and acquiring data from the field. And of course, as we heard before from Dean and myself, this is quite the endeavor. Of course, it's complex, but it goes a long ways into providing that confidence into the model both to you as the OEM or consultant, and finally the CVA or the certifying body. So let's delve a little bit into pre-processing and post-processing within the workflow of aeroelastic modeling. This picture here is for the OpenFast code, which is made up of several different modules. They all need different input files, so that we have sub-input decks for each module. We have to get to those input files. So we have a number of pre-processing tools that are either available or that you might have to develop yourself or purchase from some vendors. And then on the right-hand side, past the simulation phase in the middle, we have the post-processing phase, where we're trying to, again, crunch our time series that we have produced through our simulations toward something that we can use for either finite element analysis or other types of analysis that will allow us to establish the fitness of your design. And one thing that is important, like I mentioned before, is that of checking also for risks of resonance, which happens when we have forcing frequency and natural frequency overlap, or also instabilities that happen when we have negative damping ratios. So if we now look at the pre-processing phase, like I mentioned, airfoil aerodynamics is the dominant aspect here. There are some tools like Xfoil and Airfoil Prep. There are open source or freeware anyways that are very good starting points to try and describe the aerodynamics of an airfoil. But if you're coming up with a new airfoil design, likely you will need also to add information on the steady aerodynamics, and that is quite difficult to achieve. Obviously, best would be to go into a wind tunnel and do a dedicated test campaign, or use a higher order CFD model to extract that kind of information. To extract the blade and tower properties or other component stiffness mass properties, you may use a finite element tool, your preferred finite element tool. That could be ANSYS, but there are also other software programs out there like B-modes that are open source. So there's actually quite a few also for beam element types or shell element types. If you have a very slender blades, now with this tendency of going towards larger and larger rotors, you certainly have to describe the characteristics in terms of mass and stiffness with 6x6 matrices. And so that's a very involved exercise, and you need very specific tools that allow you to go from the, for instance, for the blade, from the composite layup to a description of your cross-sectional properties. And again, there are tools, some are commercial, some are open source, that require quite a bit of expertise. In the end, you want to both reach a model representation, say, for the tower, as well as this description of stiffness and inertial properties along your typical blade. Another aspect of the pre-processing is that of tuning your controller. And for that, again, the tools available are both commercial and open source, like the Roscoe Toolbox produced at NREL. Of course, with these open tools, very likely you'll have to adapt them for your specific needs, and you might have to debug some of these features that are added constantly to these tools. So again, there's quite a bit of assembly required besides, just grabbing tools from the GitHub, for example. And of course, we also have the turbulent environment to simulate. So we have to create these wind files. A tool that historically has been used at NREL and has been created at NREL is TurbSim. That's a very solid tool, very useful to create turbulent wind files for your simulations. On the post-processing side of things, we are after reaching these design driving loads for both, again, ULS and FLS. On the ULS side, again, we want to try and crunch all of our data. We have now tens of thousands of data points. And in these images and these figures down at the bottom of the slide, you can see, for example, all the circles that indicate the extreme calculated for one realization at one wind speed for a specific DLC. And then you have multiple realizations, and you have to follow the standards to bin the data properly, to average them properly, and come up with a description of the extreme, for example, or your DEL in the case of fatigue. We'll talk about that in a minute. And for each specific DLC, this binning operation is actually a little different, just like the partial safety factors to apply are a little different. So again, a lot of skills go into describing how the loads vary as a function of wind speed and as a function of DLC. In the end, as a function of DLC type, you can show images like these histograms where you can see, for example, the blade root bending moment or the blade tip to tower clearance, and you can see which design load case drives what component in particular. In the end, when you can finally extract your design driving load case and load, you can use that in a finite element tool or in any other analytical approach that you might have to show whether or not your design is safe. So the example that I have here is the shell buckling in the tower after going through this analysis and binning of all the data from all the simulations. From the fatigue limit state standpoint, the process consists of starting from your time series, subjecting them to a rainflow counting algorithm where you can extract the load spectrum in terms of number of load cycles as a function of load amplitude. And then you add the information from the material in terms of SN curves. You may or may not use a Goodwin correction that gives you the effect of a mean load about which your cycles will occur. And in the end, you can extract your damage equivalent load, which is that load amplitude that will create the same damage that all of the cycles processed through all of the simulations that you've accounted for scale throughout the 25 or 30 year lifetime of your turbine may actually produce. I mentioned that I wanted to talk a little bit about resonance and instability checks. The key aspect here is to understand that when you look at just the design of an isolated component, you have a certain response in terms of frequency natural modes. But when these components come together, like the blades come together around the hub of a turbine, then things become more complicated. The natural modes actually multiply. If you have 3 blades for each mode of an isolated blade, now you have 3 modes in the rotor, and they shift in frequency also as a function of your rotational speed. So things become quite complicated, and they also tend to couple quite a bit. In the animation, you can see an edge, that's what it's called, a regressive flapwise bending moment of the rotor. But again, like I mentioned before, you can use a Campbell diagram, which is a nice tool to look for both resonances and instabilities. And again, the check is for overlaps between forcing frequencies coming from the rotation of the rotor and its harmonics, and the natural modes that again are much more complicated and vary as a function of RPM of the rotor. And then on the other side, you look for instabilities where the damping ratios of these modes may become negative, for example. And again, there are tools that allow you to do this, but more than likely you'll have to manipulate these tools for your specific needs. When you finally get your loads, your design driving loads, then certainly you can go into an FEA. Generally speaking, again, you can use multiple tools that are available to the industry, commercial or not. But there are things to watch out for regardless of the tool that you use. For example, sensitivity to the mesh. You don't want to introduce artificial hotspots. You have to look for the boundary conditions, how you, for example, you simulate the stiffness of the boundary conditions between hub, shaft, and blades. You may have to simulate, say, a pitch bearing connected to your hub in order to represent the actual stiffness of the hub. And also you have to think about how you're going to introduce the loads into your model without artificially affecting the results and bring them away from reality. You also have to look for the correct failure criteria and for potential nonlinearities associated with the geometry or the materials that you use. The standard also calls for a static pull of the blade, and that is something that you can use and take advantage of also to validate your model, not only the FEA, but also of your aeroelastic model, for example. So in conclusion, I think it's fairly clear the design and analysis of a distributed wind technology turbine are quite complex activities. And yes, there are open source tools and we gather template models and we're trying to streamline the process as much as possible. And NREL has done a lot of work in this direction with lots of great tools out there, yet some assembly is still required. And I would say still very skillful and assembly, a complex assembly at times is still required. Verification and validation, V&V is absolutely critical to design and certification. I would encourage everyone to get familiar with these steps that are required before you hit the obstacle of certification. And take advantage of that. Take advantage of what you can do during validation to increase the confidence in your model. It will pay off in the long run, even though it's certainly a complex activity to carry on from the beginning. Aeroelastic modeling, I believe, is still the most rewarding pathway to the design. So I encourage you to explore aeroelastic modeling and also take advantage of some of these results and perhaps guidance that you may see in this forthcoming publication where we talk about state-of-the-art in aeroelastic modeling for distributed wind and recommendations for improvement of both aeroelastic modeling and standards. And with this, I'm sure everything was super clear. So these are my contacts, but if you have any questions, I'm open to trying and answering them.
Great, thanks, Rick.
Yep.
Any questions? We've got a couple here in the chat, and while people kind of pull them up, I can answer the one from Alex, which is what are the minimum requirements on certification to sell the turbine to the market, or is that illegal? So the short answer to that, and then you preview the questions in there, Rick, and you can dive in to answer the one specific to you. Alexander, the answer to that is there is no kind of legal requirement that a turbine be certified. So you can sell anything you want into the market, and if there's a buyer, there's a buyer. That being said, certainly from an NREL perspective, we are very strong proponents of certification. Not only does it protect the industry writ large, builds consumer confidence. Huge problems in the past were had with turbines that weren't certified and failed, and really poisoned the market. And then also it helps the company. I mean, there are a lot of companies that no longer exist because they built a turbine that they thought would pass certification, and then they found that it failed, and they had to replace them all, and that drove the company out of business. So I think even from a business perspective, it's worth certifying. The other thing is that there are a bunch of programs out there, like the federal tax credits, bunch of state programs, selling into federal markets. So if you want to put a turbine up at a federal facility or something of that nature, a lot of them require certification. And so you wouldn't be able to bid on those products or get state or federal incentives unless you were certified. So it's a mixed field there. But I hope that answers the question or dive in quickly if you want expansion on that. Go ahead.
Me?
Yeah, go ahead.
Yes. Okay. To what extent CFD simulation on ANSY's professional software could add to this certification?
So I think I'll pass that question off either to Brent or Rick.
Say it again, Mr. Kogan. I'm sorry, I missed the first few words
Okay,
there.
all right. We bought ANSI software for fluent CFD simulation. And we run right now about 1,000 hours of simulation, different simulation of our system. And we receive very significant results. My question is, how much the CFD simulation reflect result what we will receive in the real world, and on the real wind, and how much it will help?
I see. It's a good question. I was just trying to look through a publication on this matter, and it got pretty deep, but it dates back to a 20-year-old code comparison study of aeroelastic modeling tools as compared to the measured results from the unsteady aeroelastic turbine in the Ames wind tunnel, and they had some good results, interesting results from the CFD computations, computational fluid dynamic computation. So I'll send you a paper on that, but I'm not an expert in that field, but I've been trying to read about it. Maybe others know more.
Okay, thank you.
Yeah, that's a very open-ended question, I would say. The CFD obviously is a very critical tool and has to be used by folks that have a lot of knowledge and experience in using that specific code as well. And the validation of the results is an important aspect of that. And how do you go about doing that? It very much depends on what you're simulating, and it's not something that can be generalized.
I understand. We are working.
You can look at
Yes.
the literature.
We are working
Brent
as a
said, there's plenty
consultant.
of examples of that.
As a consultant, we are working with RANSIM. Maybe you heard about this company. It's very big CFD company. And basically what we're doing, they're teaching us how to make setting, boundary condition, and so on. And after that, they're kind of validating our result, or not validating. I would say we are running all wind velocity, let's say, from 4 meters per second to 25 meters per second. We are giving them, let's say, 14 meters per second, our result, and they're running by themselves and kind of confirming them or not confirming them. But I would say how much it can help and accelerate.
Yeah, so CFD, first and foremost, will give you an indication of the trends. So it's helpful when you're looking at fine-tuning the design, and it will give you a very good handle on these trends and on the gradients. A little less reliable on the absolute values, where you need to really nail down the output of a CFD simulation with some hard data from the field. So again, if you use it as a design tool, in that sense, it can help, but don't just get hung up on absolute value results coming from CFD, because then you may realize that you may be quite off from reality, I would say.
Okay, understand. Thank you.
Thank you. I don't see any other questions in the chat for you, Rick. Lots of good presentations, which I agree with. So thank you very much for doing that and going through that, and then the work that you're doing in that space. Are there any other questions that people have either to Rick, Dean, or Brent to cover the day, or other questions writ large. Happy to take them now.
Robert asked about ducted turbines and air elastic modeling, and ducted turbine folks from Clarkson said they've been working on it. But the question is, any work on air elastic modeling for ducted turbines?
Yeah, so not on our end. What we had to do when we collected also our template models was a survey of the market, and the most prominent models did not include ducted turbines. That not to say that they don't exist, or they're not there, just like bots. But we had to also come up with a priority list based on what we see on the market at the moment. But absolutely, having a ducted turbine in the template list would be certainly useful, generally speaking. I think there's a lot that can be done in that direction. It's great that there's Clarkson working in that direction. So yeah, we're certainly open to seeing what else can be done. Again, there are lots of opinions on different models, not just the ducted turbine. So it is what we did was, again, basing our analysis on the market and where it is right now.
Could you comment really quickly on airborne and the tools that are available for airborne wind?
Yeah, so airborne is in its nascent stage, of course, nascent stage, but it's growing fast, and there are lots of institutions working on that, especially in Europe. And we actually collected also a couple of templates for kites of different kinds of the ground gen and the airborne gen or fly gen types. And we do, and NREL obviously has worked on Kite Fast, which is an elastic code starting from fast. It was manipulated and modified to to include this capability of simulating aircraft with aircraft-like kites with fly gen type of generation. So certainly that's a very exciting aspect of I guess of air elastic modeling in general. It's an air elastic model for an aircraft, and we do have, like I said, we do have some hard models that folks can use with both KiteFest and also with another code that comes from TU Delft and Roland Schmel's group. And so I would encourage everybody interested in that. And again, looking at our forthcoming paper that has also that information in there. Great, thank you. Got a few more questions in here, and please type them in or raise your hand. From James, do insurance companies require such certification?
Yeah, that was me. I'm Jim Truslow, CBC Wind. I'm just curious as to if you were to sell a turbine to somebody and they installed it on their roof, to what extent would the company insuring that installation and the device be looking to whether or not it had the device itself has certification?
So I think there is and someone else jump in if you have thoughts on this. I don't think there's anything out there in reality. Clearly the big companies do. So for big turbines, that is considered by the insurance companies. For small turbines, they're usually covered under a homeowner's policy or something of that nature, and the insurance companies probably don't know about it. So I would say it's probably the Wild West in regards to that.
Yeah, I mean, I asked because, you know, when you go to your own insurance company and you talk to them about the fact that you might sell a unit, and they give you their questionnaires, and sometimes the questionnaires, you know, what are the industry standards?
Yeah, I certainly think the industry standards and DWIA has certainly made it clear, and the wind program and NREL have certainly made it clear that we feel certification should be a requirement for all installations. And so I think from the entities that are out there in this space, certification would be a requirement. Certainly the insurance industry probably doesn't know or care, or they don't know enough to care. But generally speaking, I think everybody would lean towards so.
They know enough in the large wind turbines, though.
Yes. Yep.
Okay.
Yep.
Okay. That's all I needed to know. Thank you.
Okay, great. No, certainly. Jacob, you had a question in regards to the standards and testing. I think you might be referring. Oh yeah, Jacob. Brent just sent the link to the paper. That's probably the best.
Yeah,
one
that's great.
there.
Yep, that's exactly what I was looking for. Thanks a lot.
Certainly.
Great.
Any other questions? Guru, go ahead. Can we use simulation as a basis for certification? Brent, do you want to, Guru, do you want to kind of follow up in voice, or just unmute yourself? Or Brent, do you want to take that
I
one?
would say, yeah, that's the Rick's presentation was basically the three pathways for designing your turbine, and the most optimized pathway towards certification, and an optimized turbine is through air elastic modeling and simulation.
Yeah. So this is Guru here. Thanks for taking my question. I was trying to type it, but so let's say I have a 10-foot windmill which we tested and we like the performance, and now we want to go for like maybe 24 feet or something more. So if we provide a simulation results for that, so would that be considered as like a basis for a certification? Because we don't want to spend money in building the physical prototype, but we can do the simulation and kind of like to provide the results. So would those results will be considered as a basis for certification or prototype development?
So that becomes thanks for the context, because that changes the context. So you can't just have simulations to get your turbine certified. You could certainly use the simulation to determine whether you have a product that might be valid for prototype design. And certainly lots of simulation. You would want to do lots of simulation on your turbine to optimize it, and certainly that is what we found within the industry, is that the days of being able to build a wind turbine in your backyard or in your garage are over, because you can do that, but you can't get it optimized enough to have a low enough cost to compete in the market space. And so using simulation gets you that optimized design, but then you do have to build it, prototype it, run it, and then put it through a certification process, which requires field testing. Now, your simulation of the turbine will help in that certification process if you've done all the loads calculations and that kind of stuff, and have a validated simulation model. That will certainly assist in your certification, but that in itself will not certify you or will not get you to a product. That's why it's a critical step in the process.
I think I asked like a certification, so I should have asked like a prototype development category. So let's say we did a simulation, and then would we be like eligible to like say eligible for getting funding for that. The question I ask is like, we get a pretty good results on simulation, which tends to be like considered as like a false claim or something like that, but we are not claiming anything beyond bed's limit or something. But the output from the simulation seems to be like very promising or like encouraging, and that's where there is a communication between the listener and the claiming personality says, oh, we have the best one or something like that. And then people say, oh, no, it's not gonna work because weight limit says we cannot go up to this point or that point. But then simulation shows some different promising results. For example, like if we compare our results with the existing windmills and we see, oh, it's 30 or maybe 40% better than them. But those are only simulation results. And is there any specific software which you consider, or anything like OpenFOAM or any other standard industry software is considered as valid for you to like say, oh, okay, these guys have done simulation. So do you verify it, or you just like say, okay, you have done and we can consider that kind of thing?
Yeah, okay, so let me take that question, but just in a second. I know that we're past our time here by a few minutes. So just for everybody else, please don't hesitate to stay on the line, and happy to take more questions, but understand that some people will have to drop off to other commitments. So just really quickly remind everybody, we're on again tomorrow at the same time, so noon Mountain Standard Time, 2 o'clock Eastern Time, and we're going to be talking about the procurement and contracting elements of CIP, the design review and evaluation. So a number of the award areas require a design review. And so Brent will be talking about that. And then we have a session on kind of other considerations for CIP, including technical support and things of that nature. And then last but not least, a more open discussion where we want feedback from all of you around CIP. And then again, on Friday, we have sessions all day on the different topical areas. So if you're interested in specific topic areas, again, we encourage you to partake in those. So again, everybody who wants to hang out here and delve into things a little bit more, please don't hesitate to do it. Do want to thank again Rick and Dean for their presentations and their support of the CIP program, and then also Brent for his work today on the presentations, and everybody who worked on the new standard, which is a great step forward for the industry. So thank you all, and we look forward to seeing you all tomorrow, for those who don't hang out here a little bit more today. So Guru, Guru, to your question, so the first part, you had a few of them in there. The first part of your question, I think, is yes. So the prototype development category is really designed. The category there is really focused on technologies that you've done a bunch of homework on, and you know you have a product that, or you feel you have a product that's really viable, but you haven't gone through prototype development or anything of that nature. And certainly extensive CFD and other modeling that demonstrates that you have a product as compared to you built something in your backyard and you've run it for a day. That is certainly helpful. And so if you've done a bunch of modeling, maybe have built scale models, maybe put them in a wind tunnel or something of that nature, but you think you have something, then certainly that fits you into the kind of the idea for the prototype development area. So I think that answers your first part of the question. And then your second part was, what design tools would we recommend as industry standard or something along those lines? And Rick, if you're on and could answer that, I think you're probably the best position to do so if you could.
Well, again, the design tools exist, and it depends on where in the design you're at. If you're still in the processing phase, for example, if you look at my presentation, it will be available. You can see some references there, and just get them online. The documentation is for open source tool. It's always a little bit sparse, but you can at least get going with what's online. If you are in the simulation phase, so you already have gathered a lot of information in terms of structural characteristics of your components and aerodynamics, then yeah, it's really, it's really up to you. I'm not here to sponsor any of those codes there, but there are pros and cons associated with each and every one of them. Again, there are some like OpenFast that are very widely used across the distributed wind world, and also in the bigger wind turbine space. And the advantage there, of course, is that you can download it, and if you can, you would compile it following the instructions that are there and learn how to use it, and that will certainly give you again, a pretty solid code to start your analysis. If you want something that is a little bit more user-friendly, then perhaps you would go towards some of the commercial packages like Bladed, for example, and they are much more production-oriented rather than R&D. So it very much depends on where you can or where you want to head with your design activities. And then for post-processing, again, my presentation also highlights some of the post-processing tools that are available out there. It's very hard to use spreadsheets nowadays. Again, you're dealing with very large wind files, very large files from wind to output files. So using spreadsheets is not very conducive to error-free results in the end. So you probably want to create your own processing scripts, and you can download something from the NREL GitHub repo under OpenFast and under Wisdom. You can find some of these post-processing tools. And again, they are very good starting tools. But like I mentioned in the presentation as well, in my talk, you might have to fiddle with them a little bit to get them to give you exactly what you want. But again, the references are all there. So it's a matter of spending some time and looking at pros and cons of the various options that are available.
Great.
So is there any help available in terms of like evaluating the model? Like, let's say we submit the CAD model or something, and NREL themselves verifies that simulation, because whatever we claim would be obviously biased or something. So does NREL also validate that simulation on their own, or that's not in the scope of their work?
Rick, can you answer that? And then there's a comment from Joe Sposi as well in regards to validated codes, which I think gets to the work that you've been doing most recently.
Yeah, so maybe let's start from Joe's questions. Yes, fast bladed are validated codes. They, however, introduce new capabilities all the time, and some of them may have not been validated, but NREL is constantly striving to get OpenFast to a level that is very reliable and that can be used again with confidence out there. But regardless of whatever code you end up using, you will have to do your own validation. You can't just rely on a generic test case. That is good for verification of the code, but not for the actual validation of your design, which again would probably require validation, as Joe says as well. And to respond to, I think, Guru, I thought that question was directed to NREL, if NREL support that. Is that correct?
So, yeah, I think so. So at a very light level, NREL can support some work on the codes, but it's very limited. Unless you submit a proposal and request for under CIP request for technical support in the development of or validation of a model that you have developed. So we have done some of that with CIP awardees where we do provide that technical support, but it's under the banner of CIP, not something that can be provided outside of CIP as a general rule.
Okay. So my question is like, let's say we submitted a proposal under CIP, maybe prototype development or design, and we claimed something, okay, this is what the efficiency or output is from our windmill. So do you verify it in some way doing your own simulations, or it's just purely based on your past experience with windmill saying that, okay, wind turbines cannot go beyond this limit or something, so this is
right,
or something like that?
So generally speaking, the way that we would prefer to do that is that you obtain that expertise yourself through a subcontractor, and so someone on your team would be working with the code and the validation of the code. NREL, as part of the design review process that we'll talk about tomorrow, would then look at the results of the code and the results of the simulations that you do, and talk through with your team whether there was anything that we saw that was being kind of unusual. We would not run a tool to validate the work that you're doing, because we're presuming that you and your team are doing that in a competent fashion, because we have no question that you wouldn't. Again, NREL would do that as part of a CIP award. What really matters, though, is that the certification organization that you're working with would accept that validation. And so you would want to be, depending on where you were in the design process, you would want to be discussing with a certification entity about what would be needed to validate the code to allow it to be certified. And generally speaking, you're going to want to do that earlier rather than later, because you want to make sure that the turbine that you design is designed to meet the certification requirements, not design your turbine and then after you've done prototype testing and all of that kind of stuff, realize that the turbine that you have designed won't meet the certification requirements because you haven't talked to someone who has experience with certification. So even at the really beginning stages of the development process of a new turbine, you really do want to be engaging with a really good modeler who knows how to model distributed wind turbines, depending on what configuration you have, as well as someone who really knows the certification process for your technology, so that you can design your turbine for certification from the beginning, instead of playing catch up and trying to do that later. And whether you have that expertise on your team as someone who wants to come up to speed and do all of this, or whether you hire that as a subcontractor from the people that are doing this, that's certainly your choice. But the idea is that through CIP, if you're successful in writing a proposal, that NREL and the Department of Energy helps cover the cost of that, which I know is a big hurdle if you are trying to do it by yourself.
So another question was like, do we get any feedback on the last year's submission, like why it was kind of not considered or like failed to meet? Okay.
So the thing to do is follow up with Kendall Jackson, and we're trying to organize those calls as soon as possible after the new year. So I mean now through the new year and in January. So follow up with Kendall and let her know, Kendall Jackson, and let her know that you still have interest in getting a review of your last submissions, and we will be scheduling those very soon.
Sure, that would help us like the next submission.
Good. Okay, very good. All right.
Thanks for
We're oh, of course, that's why we're here. All right, thank you, everybody.
Thanks,
any
Ian.
final questions? If not, we'll see you all tomorrow. Very good. Thanks, everybody. Have a great afternoon and evening.
Thank you. Bye-bye.
Bye, everybody.